PeatSAR, a satellite mission aimed at measuring soil moisture in tropical peatlands, a key property that will help us monitor their extent, changes, and carbon storage. This information will prove to be invaluable when understanding the role of peatlands in the carbon cycle and the relevant knock-on effects on climate change. Measuring peatlands is a very challenging task due to their complex nature. Matter of fact, there is actually not an accepted definition of peatland in terms of organic matter content nor depth, so this leaves considerable uncertainty on the spatial extent and carbon stock of peatlands on national to global scales, as most estimates we currently have are just based on coarse data or like rough national inventories. So we need spatial resolutions less than 1 kilometer. Not only that, but satellites are very important to continuously examine the state of the peatland environment, both repeatedly and systematically. In conjunction with accurate in situ field observations, they allow us to rapidly update peat maps and monitor the effects of climate change on peat degradation, among other things. So what exactly are we going to be measuring? Well, as I mentioned before, peatlands are a very complex system and they're affected by many factors. However, of these many, soil moisture correlates best with both peatland and fits in well with major research topics. However, it's worth noting that these factors aren't exclusive proxies for peatland cover estimation, and we need information on all of them to truly understand peatlands and get the full picture. Soil moisture does provide key biophysical information about peatlands, and this information can be used in conjunction with data from other peatland variables retrieved from different missions to help us give us, as I said, the full picture on peatland dynamics. And just as a bonus there, soil moisture will also give us the most direct measure of peat flammability that would be invaluable in fire monitoring studies in the tropics. This data retrieval of soil moisture is feasible, and currently there's a lack of it in tropical peatland due to associated difficulties that we had previously. So there's a big need for this data. So how exactly are we going to measure soil moisture? Well, we're going to be using radar data, and more specifically, we're going to be using long-wave L-band radar data, which has been suggested as the best by many reviews and different meta-analysis. The advantage of this data is that it will allow us to penetrate to the dense tropical canopy that we said was difficult to do so before, but more on the measurement method later on in this presentation. Our mission is of great relevance and aligns with goals set out by the European Space Agency. More specifically, it will contribute to Section 4 in Volume 1 of their scientific strategy and challenges A2 and L1 in Volume 2 of their scientific strategy, allowing us to monitor peatlands, their carbon stocks, their role in climate change mitigation by sequestering carbon, and the effects that us as humans are having on them. These papers support our proof of concept as they illustrate both the feasibility and the relevance of our mission, as well as giving us the basis and the foundational knowledge that we use to design the more technical aspect of this mission, which we will talk about right now.
So for the technical side of our mission, we have decided to use active radar system, in particular synthetic aperture radar with L-band frequency, which will allow us to make measurements irrespective of clouds or the cloud cover, or during nighttime when it wouldn't be possible for optical sensors. Furthermore, it will allow us to penetrate the canopy in tropical regions, which is a common problem for shorter wavelengths, both of optical and shorter wavelength of SAR, and thus reliably obtain soil moisture estimates from below the canopy, allowing us to estimate the size and extent of peatlands in the tropics. To improve our retrieval of soil moisture estimates, we will use synthetic aperture radar polarimetry, so the polarization of the waves that are emitted through the active sensor and also returned back. We'll use full polarization, so the combination of copolarized signal and cross-polarized signal in both vertical and horizontal direction. This will be done in order to correct for the effect of vegetation and surface roughness, which are often the problematic parts in estimating soil moisture below the canopy. However, they are sensitive to different types of polarization, so in particular, surface roughness and vegetation are sensitive to cross-polarized signal, and soil moisture is sensitive to co-polarized signal. So by combining these, we can reduce the uncertainty in the measurements of soil moisture. Our satellite will all orbit the Earth in the low Earth circular orbit at an altitude of approximately 400 kilometers. Since the focus of our mission is on the tropical regions, we have decided to restrain our satellite orbit to 35 degrees north and south of the equator, which will improve our temporal resolution and the revisit time. This has been done previously by the Tropical Rainforest Measuring Mission. The biggest disadvantage of this orbit is that it is not sun-synchronous, and therefore revisits to the exactly same location are relatively infrequent, and we'll be measuring on our variables at different times of the days when the revisit happens, which can be disadvantageous in some applications. However, we believe this will be offset by the frequent coverage of the orbited area, and a significant amount of data will be produced which will offset this issue. In terms of viewing geometry, we'll be using an imaging SAR system, so we will need to use a side-looking geometry, allowing us to construct an image to differential return time of the signal from different parts of the scanned area. We will use either a simple side-looking, or we are also considering using a conical scanning geometry, which was previously used by the ASMAP mission, and will allow us to keep the property of looking sideways but potentially providing faster coverage of our area. The products that our satellites will produce. The level 1 will be a high-resolution geolocated radar backscatter signal, which will be possible to use by scientists who wish to apply their own algorithms for retrieval of soil moisture or potentially other variables. And level 2, which will be analysis-ready soil moisture estimate derived from a level 1 backscatter, to using polarimetric properties and appropriate algorithms. We are aiming to achieve accuracy of approximately plus minus 10%, a resolution of 10 meters to allow us for high resolution mapping of soil moisture and peatlands. Lastly, our mission will be complementary to many other missions which had similar purpose of retrieving soil moisture. So in particular, soil moisture has been previously retrieved by mostly passive sensors such as ESMOS and ASMAP, which can only obtain soil moisture estimates at a very coarse resolution. So our satellite will improve on this, and potentially by combining the data with the previous instruments, we'll be able to derive very high resolution maps of tropical peatlands through soil moisture. Our mission will be also complementary to the existing active SAR missions, which however have global coverage and usually different purposes, which makes it difficult for them to be applied for peatlands alone, and also for the future missions with different focus such as biomass or NISAR that will focus on measuring biomass and ecosystem instead of soil moisture alone.